All right, so we're back for part two of the slope deflection equation method example, and here I took the liberty of writing out slope deflection equations and bringing my blown up schematic with me again, and just writing the slope generic form of the slope deflection equation here. And the thing to remember when you write these slope deflection equations is that there's two equations per member, right here, per member. So first and foremost, member AB, right here. Member AB, right here. So here I would just start right here. So for MAB, I would have 2EI over LAB times 2 theta A plus theta B minus 3 psi AB plus FEM AB. And that would describe my internal moment right here, AB. Then I look at MBA, which is this side right here, which is 2EI over LAB, again, the same length, 2 theta B plus theta A minus 3 psi BA plus FEM BA right here. And I like this form because I can just look at the equation I'm looking at and just plug in, substitute, A for I and B for J, and just plug and chug right through right here. And the other thing to note is that point A right here is fixed, and therefore the rotation is 0. So that's 0. That's nice. Boom. And there is no support settlement of any kind. So therefore there's no rigid body rotation. So this psi AB, these are also 0. And what it leaves me with is just it's a pretty simple equation, really, that if I plugged and chugged some numbers here through this 2EI over L, it would give me 2 over 10 meters, which is the length of AB, times EI, times theta B, minus 12.5 kilonewton meters right there. And then here, this would be the same 2 over 10 meters, or 0.2 over meter, EI times theta B plus 12.5 kilonewton meters right there. And that's member AB. Now we just go on to member BC right here. And member BC over here is, again, two equations per member. So MBC is 2EI over LBC, 2 theta B plus theta C minus 3 psi BC plus the fixed end moment at BC. Okay, there's that. And then MCB, and you can fast forward this if you want. It's a no. It's just the same. It's just repetitive. And that's the advantage of these slope deflection equations, is that you can just repeat this process over and over. But also the reality is that, if you're going to do this, if you're going to do structural analysis with so many degrees of freedom or so many degrees of it's just better to use a computer. But you got to know what the computer does anyway, right? Or at least try to check some answers. But so here, FEMCB. All right, so here we've got, hopefully that looks good. You plug and chug, or you realize that point C is fixed. So this is 0. Again, no rigid body translation because there's no rotation, no rigid body rotation because there's no support settlement. So 0, 0, and all we're left with is just a bunch of theta B's, really. And so this becomes 2 over 20 this time. Oh, I messed up big time right here. This was 2 times 2. This should have been a 4 right there. So here, this is 2 times 2. That's 4 over 20 meters EI times theta B. And then plus the fixed end moment for BC, which is minus 33.333 kilonewton meters. And this is equal to 2 over 20 meters times EI times theta B plus 33.333 kilonewton meter. All right. So hopefully that's, and these are my slope deflection equations. Now we're ready to move forward once we have those, and once you can agree that these are okay. Now we just need our equilibrium equation at the joint. So let's see, just in terms of process here, we've done the NOKs, or unknown displacements, blow up the structure, FEM, the fixed end moments, the slope deflection equations. Now we're at equilibrium, and this is equilibrium of the joint. And really, there's only one NOK, so that really tells us that all we need is one equilibrium equation. And that equilibrium equation will come from joint B, And here, so we'll call this, what step was this? This is process 4, 5. So this is equilibrium at the joint, okay? And here at joint B, it is, let's see, joint B. And this is sum of the moments about point B equal to 0. And really what I'm doing is, if I look at that blown up structure again, is I'm taking equilibrium about here. I'm taking moment of equilibrium about this right there. And that just tells me that by this equation right here, just tells me that MBC plus, let's see, that was MBA, I believe. MBA is equal to 0. All right. So now all I got to do is take my slope deflection equations, and in this case here is this MBA equation and MBC equation, and just plug and chug into my equilibrium equation. So here, if I go ahead and do that, let's see, I'm going to solve. And what I'm going to be doing here is really step 6, which is solve for the unknown displacement. Solve for unknown displacement, or displacements plural, right? But if I go ahead and solve for this here, I'm just going to plug and chug. This will be 4 over 10 meters times EI times theta B plus 12.5 kilonewton meters plus 4 over 20 meters times EI times theta B minus 33.333 kilonewton meters equal to 0. And that of algebra and stuff, this is what, 0.4, and this is 0.2. So this is 0.6 EI times theta B, which is equal to, and I just worked the math for that, and that's 20.833. Let's see here. Don't forget the divide by meters here, and this would be kilonewton meter like this. And then again, if I solve for theta B, which is that unknown displacement, this is 34.722 over EI kilonewton meter squared. And you know the units are good because the units of EI are force times length squared right here. And so that means the units will cancel out, and then and as per rotation, it's dimensionless, okay? So here, that's that theta B is this displacement. Yes, right there. And now all you've got to do to get the internal moments, these moments here, is plug and chug. So here, let's put it in red. Plug, it's not really a step at all. Plug and chug into slope deflection equations to calculate the moments, to calculate all the other internal moments right here, MIJs, whatever they are. So if I go through, so I'll do one for you, and I'll just give you the numbers for the rest. MAB is 2 over 10 meters times EI times 34.722 EI kilonewton meters squared minus 12.5 kilonewton meters. And this, if I, boom, cancel that out, meter, cancel that out. And this will give me that the MAB is hopefully a number that makes sense. Yes, it's going to be in units of kilonewton meter, and this is minus 5.556 kilonewton meter. And again, if you just go through and solve the rest, you can fast forward this here, 26.389 kilonewton meter. And here, MBC, if you plug and chug for this, is minus 26.389 kilonewton meter. Hopefully that makes sense to you. And MCB is equal to 36.805 kilonewton meters. Okay, and the negative sign just indicates that it should be drawn the opposite way from your blown up structure. Okay, that negative sign there, that is opposite. This negative is opposite the way you've drawn it in your blown up structure. So hopefully this is pretty good for the slope deflection method. And in the last part, if it's not clear to you already, we're going to draw these moments back onto the blown up structure in the right sense, if you will, and solve for the other internal loads, namely shears, and draw the shear moment diagrams. All right, so I'll see you in part 3 if you need it. See ya.